Okay, I wanted to explain Dalton's law as well as Henry's law, and these are gas laws which have an effect on dissolving gas into blood, as well as kind of how gases exert partial pressures to contribute to an overall pressure, and that will help us determine certain physiological states with different equations if we can know those two laws. So with Dalton's law, we know that individual gases exert partial pressures. What does that mean? So in the atmosphere, we're going to have 760 millimeters of mercury as a pressure total. So that's a combination of oxygen, nitrogen, carbon dioxide, and a couple other gases, and all of those will total up to equal 760. So over here I have this equation. We have a partial pressure 1, partial pressure 2, and they add up to our total pressure our total pressure of atmospheric pressure. We can determine what our partial pressures are by taking percentages of this overall pressure. So let's say partial pressure 2 is from oxygen. If we took a percentage of partial pressure from the overall atmospheric pressure, say it's 21% oxygen from the atmosphere, then 21% of 760 would come out to our partial pressure. So you can do the same with nitrogen, same with carbon dioxide. Each one of those will have a percentage of concentration of the overall pressure, and that's Dalton's law helps us figure out those different pressures of each gas. Moving down to Henry's law, there's a couple factors that we need to consider, but overall, Henry's law pertains to gas dissolving in a liquid. So if you've ever had a root beer or something like that, you know that there is gas within your fizzy drink. So we know that gases can dissolve in liquid. The first factor we take into consideration is the partial pressure of the gas surrounding a liquid. So in this container, we have a plunger, which is pushing down gas on top of a liquid. If that pressure is exerting enough, then it will diffuse or dissolve into the liquid. We also have to take into account the solubility of gas in liquid. So carbon dioxide will dissolve into blood quite readily, but oxygen will not. So different gases have different properties wherein they determine, do I want to dissolve into this liquid or not? CO2 will enter the blood pretty quickly because of its partial pressure and its solubility. So that kind of covers Dalton's law and Henry's law, and as well as why there are partial pressures of oxygen and CO2 and how that helps with moving oxygen and carbon dioxide within the blood. Let's move over to this alveolar gas equation. Then this will help us know how much oxygen is in the alveoli at any given point. We can't stick a probe down in someone's lungs and take a sample, because that's just impractical. So instead we have to turn to math and use pressures of carbon dioxide leaving the alveoli to determine how much oxygen is in the alveoli. And we can look at this equation and flip it around to find that out. So a ratio of carbon dioxide to oxygen is usually 0.85, and that comes from another rate. Our ventilation perfusion ratio is just like how much carbon dioxide and oxygen is getting exchanged. So if we look at these numbers, or this equation, we have your percentage of oxygen in the atmosphere. So this is atmospheric oxygen. Usually it comes out to 21%. We just talked about partial pressures on the previous page. And if we multiply that times atmospheric pressure minus the vapor pressure of water, so within the alveoli we'll have water, and that has a vapor pressure which will exert on the alveoli. So we need to take that out of our total atmospheric pressure to get an accurate reading. So we'll multiply the percentage times that difference, and then we'll take that difference minus this this equation here, which is our alveolar pressure of carbon dioxide over R. And that essentially equates to O2 being equal to VCO2 over R. So that's essentially finding out O2 in general. So we have atmospheric oxygen, or oxygen we ideally would find in the alveoli, and then we have oxygen that we actually find in the alveoli, or idealized, and then we subtract the two and we will come out with a partial pressure of oxygen in the alveolus. So this equation works to help us know how much oxygen is in the alveolus. There was something else that I needed to explain. Essentially, if this is low, that means that something is wrong, that we're not diffusing oxygen into the blood correctly, or we have too much CO2 coming out, which means we might be in a state of alkalosis or acidosis. This equation will help us know how much exchange we're having within the alveoli.